So, hey, welcome to the first edition of Frontend Engineering Meetup in Productboard. It's really nice to see some faces finally after a long time. Last time we had online meetup, so it's great addition to have people here. And for today, I prepared a talk loading 40 megabytes of JSON on initial load, where I'm going to talk about evolution of data fetching in Productboard. It sounds a little bit catchy, right? But what can you do with loading 40 megabytes of JSON? Just don't do it. So this is the end of this talk, and see you next time. No, I'm just kidding, but I know that most of you would say this. I'm going to tell you more about it later on, but first let me introduce myself. I am Lukáš Huvar. I am a software engineer in Productboard. Right now, working in a developer experience team in Platform Tribe. I joined Productboard 2 years ago and work on various topics in our front-end architecture. You can find me online mostly by my nickname Huvik. And before joining Productboard, I was working in Vercel as a Next.js core developer, where I developed famous API routes. And before Vercel, I was working in Prisma, where I created first version of data editor right now called Prisma Admin. And in my free time, I enjoy music, bouldering, and spending time with my family as a dad. And before we jump on the agenda for today, I just want to mention that this talk is another episode of the front-end performance at Productboard. You can check the last talk, Every Millisecond Matters, where I'll talk about how to improve the time to first byte. Sneak peek, we are using Cloudflare workers for serving index HTML and moving closer to our customers, serving it from the edge. So what I'm going to talk about today. First of all, I'm going to introduce Productboard so we know how it works and what kind of data we are dealing with. Then there will be a section about data fetching evolution, what we are doing, what we tried, and what we are going to as the next steps. And in the last section, I will tell you how we try to get as much possible from our current data fetching strategy. So what is Productboard? Productboard helps product manager understand what customers need, prioritize what to build next, and rely everyone around the roadmap. So what can you do with Productboard? You can align your team and easily tailor roadmaps for anyone in few clicks. Use the data to help prioritize what's best for your customers and business. Understand your customers by centralizing all sources of feedback in one place. And share what's planned and close the feedback loop with your customers. And whatever your team work, bring it all together here in the Productboard with our integration and APIs. As you can see, Productboard is really a data-heavy platform. And this brings us to the second part of this talk, and that is data fetching evolution in Productboard. Productboard started as React single-page application. Right now, we have around 640,000 lines of code. We had just one Ruby on Rails backend with APIs, and it was only source of the data. As the company grew, there were a need for more services to make teams more independent. Because of that, we introduced API gateways and started to creating microservices behind it. These services are powering various parts of the Productboard. This brings us to the current backend service and stacks we are using in Productboard at the beginning of this year. As you can see, we already have a lot of services in place. We have a plan to divide these services more into the tribes, and here you can see the possible future for us. As you can see, we are not increasing number of different stacks, but we are sticking with the already proven one, but only increasing number of the services. So Productboard was built on reference architecture, reference implementation of Flux architecture created by Facebook, or now called Meta. There was no Redux or any other different similar framework for storing the data. And for people not familiar with Flux, we have data in Flux flows in one direction. We have an action that is distributed to the dispatcher, and this dispatcher distributes this action to the stores. These stores emit change events, and we have views that are listening to these changes and propagate data to them. Later on in views, we can events creates actions, and these are dispatched again by dispatchers, and so on. We have one special, in our Flux architecture, we have a lot of different kinds of stores, but we have one special one, what is called REST collection store. As one would expect, this store works with REST API. It holds normalized data for one data model inside of the database. Here you can see one simple constructor with the name of the database model inside of the database, and that's it. And this store has a lot of features built in by default. For example, you can have optimistic updates, real-time updates through WebSockets, and so on. This store is synchronous, and all updates are done through WebSockets or services that dispatches actions like create, update, or delete. Now let's see it in big picture how it works. When Johnny starts loading the product board, it requests data from our Ruby on Rails monolith. These data are transferred as one big blob of JSON and stored inside Flux stores. We can say this Flux stores works as local cache. When James creates a new feature inside Productboard, Ruby on Rails distributes messages through through Pusher. Pusher is message bus built on top of WebSockets. Our Flux stores are listening to these messages and updating their internal states of the store. In that way, James created a new feature inside of Johnny's product boards. These updates are happening in real time. So let's talk about the pros of this solution. Our team had great developer velocity with this solution. It was really easy to ship new features with that. Everyone loves real time, so do we. And working with normalized data is super sweet because it's so simple to mutate them and update them and do something with it. On other hand, we had some problems with it. When the size of the data grew, the initial load started to suffer, but most users were using Productboard as long-running instances, so it wasn't that big problem. This architecture had a lot of logic on front-end, mostly relationships, and we were doing some computations too. And it was not possible to fetch data only what user needed, so we needed to transfer more data over the wire. We are monitoring how our customers load Productboard. We collect a lot of different metrics, but we are going to look into how long it takes our users to load the workspace. When user loads workspaces, these requests are hitting Ruby on Rails, and we know how much data we transfer for each model. You can see it on the slide. With that, we know what model accounts for the biggest size in our payload, and we can see what we should focus on next, what we could improve, and so on. Now let's back to the 40 megabyte of JSON. When we are talking about 40 megabyte of JSON, it's not size transferred over the wire, but raw JSON. This amount of data was only for big customers and mainly for our Productboard space, because our company is 7 or 8 years old, so we have a lot of data. As mentioned before, we were using normalized data, and if you enable compression on the normalized data, you get great results. As you can see, for example, 21 megabytes of raw JSON are compressed to 4 megabytes transfer of the network. And we call this abstraction in Productboard all JSON. We knew that this is not going to scale, but we tried to get as much as possible from this implementation because it provides us great value, and it was really great for building early startup because you need to do fast iteration and have great developer experiences, and we got everything from that. So it was great for early startup. But as we grew, it didn't scale. So at the beginning, Productboard, we had customers that didn't have a lot of data. As we move up market, we had bigger and bigger customers that were processing more and more data. Our current data fetching strategy started to hit limits. We had a few aces in our sleeves, but we knew that this is not going to be enough for the long run, and it's not going to scale. At this point, you can decide what to do next. So basically, you can start complete rewrite of data fetching and stop delivering new features, and you stop giving value to your customers. Or you can incremental adopt a new data fetching strategy, but there is still a problem with growing customers. So we decided to do incremental adoption because we are a product-driven company, and we need to deliver value to our customers. We wanted to prolong this runway of the migration so we can buy more time for it. Because of that, we wanted to squeeze as much as possible from our current Flux data fetching strategy. With that in mind, we set a new strategy. That's all new feature need to implement their own data fetching without adding a new data model inside of our all JSON. Currently, we have 106 data models inside of all JSON, but we are slowly reducing the number of the models there. But most likely, we are going to keep it for some time because it would require a lot of work and refactoring, but we need to focus on something else too. Now let's talk what didn't work for us in Productboard. Even though jQuery is great, it didn't work for us because we were lacking normalized cache. Pagination doesn't work as we wanted, and updating data in multiple places is not a trivial topic. We were lacking more standardization around React Query because keeping everything up to date from documentation and best practices requires a lot of work for platform teams. And we rather spend that time on something else than create framework around the library. We tried backend for frontends, but we didn't like that how long it takes to create a new feature. And sharing data for this abstraction is a bad idea, and it's reduce your time for creating new features because of that. This brings us to our final destination, which is GraphQL. We created a proof of concept in fourth quarter last year, and now all new features are built on top of GraphQL. We are using federated GraphQL on backend, mainly with Netflix DGS. On frontend, we are using Relay, and internally, we call this ecosystem Drink. And if this sounds interesting to you, contact me or any of my colleagues, and yes, we are hiring. And somebody else is going to talk about our GraphQL journey, so stay tuned. And so this brings us to the last part of this talk, where I'm going to explain some strategies we implemented for getting as much as possible from our Flux data fetching strategy. We wanted to prolong our migration path as much as possible, so we have more time to migrate. So we deployed multiple enhancements that fixed some big issues we were facing. First of them was lazy loading part of store that was delivered by product teams. They identified what kind of stores could be pressure load. These were mostly long descriptions that were created by rich format editing, and we are loading description in lazy method when you can see it. You can see on the GIF or GIF. Next one was lazy loading parts of store. Sorry. Here you can see a whole week followed by 3 days where we are loading full feature model. And after that, we have 2 days where we started loading description lazily. So as you can see, we reduced the transported size almost by the half of that. Next one is lazy loading stores. These were, again, delivered by product teams. With this optimization, we could remove the modules from our JSON and stop sending data altogether. With lazy loading stores, we get data only where we need it and when we need it. Another one was splitting one request to multiple requests. And it was delivered by platform team. And we were sending most of the data in one request, but for big spaces, better to send it in multiple requests. But we had the question, is it good for small spaces too? No, it isn't. But anyways, we turn it on even for small spaces because it was improvements for everyone. And we improve P90 by more than 1 second, what was great improvement for this small change. Another cool optimization was delivered by product team. We wanted to show detail of the feature as fast as possible. They created a minimal React application that is mimicking how Productboard looks like. And as you can see, when we load Productboard, now you have the minimal React application, and under the hood, the main application is still loading. And after the main application loads, the minimal application unmounts from the view. So basically, we could reduce the time to see the detail, for example, for feature and other things. It's a little bit hacky, but it was really problematic to untangle some parts of code, so we went this way. But we are going to do it a little bit different in the future. Prefetching data request was delivered by platform team. So we are rendering our static template on the edge, and until you start executing JavaScript, you need to wait, download it, and parse it. So you prolong when you can start fetching the data. So we added preloading inside of the HTML template. So when you start fetching data, you start it even before you start parsing, processing JavaScript, so it's faster. And it could be anywhere up to 1 second, depends how much JavaScript you are sending to your users. Fetching only data we need for a screen was delivered by platform team. So we have array of routes. This array works as mapper between routes and models that are required for that route. And if there is a route with a match, if there is match, we load required data models, then insert it to the stores and hide the loading screen. And in the background, we are still getting the rest of the data. So we create this blocking promise that is blocking the rest of the UI until we load the rest of the data. So we can show the parts application faster than other parts of the application. And if we don't match the route, we get all the data and do the same thing with inserting to the store and hiding the loading. This optimization sounds simple, but there is a problem with data dependencies because, for example, on some screens, there are dynamic configurations, and these change what data requirements you have for each screen. So it's a little bit difficult to know which kind of data you need for each screen. So it's not that easy to preload them. This brings us to another optimization, and it's smart prefetching by route. And it's similar as the last one, but it puts preloading to the edge. So instead of having it statically in the index HTML, we are creating it dynamically. On the edge, we are using Cloudflare Workers because it works for us and it's a great platform. And in Workers, you have Even Listener, where you listen to incoming requests. And when we get requests, we fetch HTML from cache. And if we don't hit the cache, we get it from key value store, where we hold our index HTML templates. And then we preload data. We dynamically insert the preload links inside of the indexed HTML with our preloader. And in preloader, we create links by models. And in preload, we have the exact same logic as we have in the main application. So basically, we have the same requested URLs in the main application and on the edge statically. This brings us to the another optimization, recompute optimal fetching. We have this optimization still in our pocket, and we didn't implement it yet because each space has different data distributions, and we would need to periodically check what kind of data they have and create best fetching strategy for them in that manner. And we will load the data depending on the strategy for each space. And the last optimization is still in our bag. It's local cache with config resolution. So the basic flow would look the same as before. So Johnny would get the data from Ruby on Rails, store in the Flux stores. And with that, we wouldn't keep the data only in the session memory, but store it in index DB2. So next time when Johnny loads the product board, we would get diff of the local data and the data we hold in our Ruby on Rails monolith. This sounds cool, but there are a lot of problems like conflict resolution and security issues and what to do when you lost connection with your with internet and so on. So we are working on it, but it will take some time most likely. And that's it. So let's summarize what we talk about today. So developer velocity is key in early startups, so you can iterate fast on your product and deliver value to your customers. There is no silver bullet solution. It varies on size of your company and what are you trying to build and what are the product requirements. So you need to think hard about it. And you can prolong the migration runway if you create smart solution that is going to reduce your problems temporarily until you have proper solution and you can migrate. And that's it for today. And I hope you like it. And now it's time for your questions. Are we going to do questions first from the audience?
I think it's okay if you do the screen first.
So how do you handle breaking changes in the front-end data model, property name changes that are then propagated to the backend API? Do you force browsers reload? We are trying to not to make breaking changes because it's problematic. We could do force reload, but like I said, we stopped to create any new features on top of all JSON or this strategy. So basically, there is freeze, so we are not dealing with this breaking changes. But before we had this force reload for the applications. Did you compare preload via link with HTTP server push? No, we didn't. Invalidating query and batch fetching via React query was not sufficient. No, because we have data in a lot of different places, and if you need, for example, update one data model in some query, it's kind of difficult to find where you need to update it, and if you already have the data inside of the cache. And we tried to create abstraction on top of React query to handle these cases, but it was you would need to iterate through the whole query and so on and update it there, so it wasn't great for us. Like, normalized cache is better in that way. So have you graphs on front end? Do you consider using true graph database on backend? No, we didn't think about using graph database on the backend because we are sticking with Postgres right now for most of the services. So we are trying to build the Productboard in distributor manner. So basically, each service has its own database, and they are syncing through Kafka and so on. So we don't want to have like one solution, one database on backend, because different databases can work for different use cases. And what is the sum of all the optimizations? We bought some time for our migration to GraphQL, and we are still trying to create more optimizations because, like I said, Productboard has 640,000 lines of code, what is a lot, and you would need to refactor a lot of things to move it to the next thing for us, what is GraphQL. So basically, we try to buy as much as time for us to do discovery, migration, and so on. And it takes a lot of time in kind of big companies, so yeah. And we save some megabytes for our end users, so the Productboard floats faster for them. So it's win-win for everyone. And yeah, that's it. Maybe some questions from audience.
Okay, speak to the box.
So you use Postgres and Ruby on Rails?
For some part of our stack, yes, but we don't use only Ruby on Rails. We have Kotlin microservices, Node.js microservices. There are some machine learnings built on top of Python. And am I missing something? No, that's it. And I don't know what kind of databases is each service using, but I think most of them are using Postgres. I know we are using Elasticsearch, and other than that, I'm not sure. Maybe you can ask someone else from the backend if there is anyone. Okay, looks like that's it for me. Thank you, and see you next time.